Exponents, or powers, can be thought of as the number of times you multiply something by itself. So x squared tells us that we multiply x by itself 2 times. X plus 3 to the 99th power would mean that you would multiply x plus 3 by itself 99 times. Exponents have their own set of properties. When you have the same base, you can follow the following properties. A to the power of m times a to the power of n equals a to the power of m plus n. Or a to the power of m to the power of n equals a to the power of m times n. When you have two things multiplied inside of your power, a times b to the n, you can separate those into being a to the n times b to the n. When you have a negative power, that takes the number and puts it in the denominator. So a to the negative n equals 1 over a to the n. This works for all numbers except for n equals 0. Or if you have something being divided to a power, as in a over b to the m, that can be written as a to the m over b to the m. Similarly, if you have a over b to the negative n, you can flip that fraction and have b over a to the n, which would then be further written as b to the n over a to the n. We can also say that any number to the 0 power will be equal to 1 except for 0. We can also say that if you're dividing two things with the same base but different exponents, you could say a to the m divided by a to the n equals a to the m minus n. Take a minute to pause the video now and try solving the following examples. Let's work through this example. So we're going to use our rules of exponents. So x to the 0 becomes 1, and then x squared to the third becomes x to the 6th, and then x to the second power times x to the 1/2 power becomes x. So we have 1 times x to the 6th divided by x. So we end up with x to the 5th. For this problem, our x to the third power divided by x to the 1/2 becomes x to the power of 3 minus 1/2, and then the x to the 3/2 times x to the 0 times x to the 7th becomes x to the 3/2 times x to the 7th. So we have x to the 3/2 minus 1/2 plus 3/2 plus 7. So we end up with x to the 11th. For this problem, we're going to first bring down anything with a negative exponent. So we're left with x over x plus 1 plus 2x over x minus 4. Then, to combine the two fractions, we're going to find a common denominator. So in this case, there's no common denominator between x plus 1 and x minus 4 except x plus 1 times x minus 4. So bringing the two fractions together, we have x times x minus 4 plus 2x times x plus 1 over x plus 1 times x minus 4. Simplifying, we get x squared minus 4x plus 2x squared plus 2x. We leave the denominator the same because that's usually how we do it in calculus later on. So we end up with 3 squared minus 2x over x plus 1 times x minus 4. We can simplify this one step further by pulling out an x in the numerator, leaving x times 3x minus 2 over x plus 1 times x minus 4. In this example, we're going to use the fact that this is a negative exponent to flip, so then we'll end up with x minus 3 times x squared over x squared y to the negative 1 to the 4th power. So then we can flip the negative exponents and bring the fractions together with the similar terms, and so we'll end up with y to the 3rd over x to the 5th to the 4th, and then multiplying in that 4th power, we end up with y to the 12th over x to the 20th. For this example, we're going to flip the second fraction, since dividing by a fraction can be the same as multiplying by the reciprocal. So we end up with 4x to the negative 3rd times y to the 4th z to the 6th over 12x squared y times 5x y to the negative 1 over 15x to the 3rd y to the negative 2nd to the 2nd power. So then we can simplify each of the two fractions. So we end up with y to the 3rd z to the 6th over 3x to the 5th times y over 3x squared to the 2nd power. Putting in that 2nd power, we again have y to the 3rd z to the 6th over 3x to the 5th times y to the 2nd over 9x to the 4th. Putting that all together, we have y to the 5th z to the 6th over 27x to the 9th. Radicals or roots can be thought of as the opposite of power. You are looking for some number that you would have multiplied a specific number of times to get the number that you were taking the root of. Square root of 4 is 2 because you need to multiply 2 by itself 2 times to get 4. Radicals can also be written as fractional exponents. Then you can use the rules of exponents. For example, square root of 2 can be written as 2 to the 1/2 power. The numerator of the fractional exponent is the power. The denominator is the root. You can remember this by thinking of how the root is on the bottom of a tree. Example, x to the 3/4 is saying to take x to the power of 3 and take the 4th root. When solving, you can take the root first or second, but we usually take the root first so that we are left with a smaller number to take the power of. Example, 4 to the 3/2 would take the root first to get 2 to the 3rd power, which is 8, rather than trying to take the square root of 64. Take a minute to pause the video now and try solving the following examples. With something to a fractional exponent, we're going to take the root first. So here, we can take the 4th root of 16 over 81 first, and then take it to the 5th power. So we end up with 2/3 to the 5th power, or this goes a lot faster than if we tried to take 16 over 81 to the 5th and then take the 4th root of that. For this example, all we need to do is take the 4th root of 625, so we get 5. For this example, we take the third root of 125 over 216 and then take that to the second power. So, taking the third root, we get 5/6 to the second power is 25 over 36. Multiplying polynomials can get messy pretty quickly. Here are a few methods that you can try. First being the FOIL method. The box method for multiplying two polynomials. Draw a grid which has the same number of columns as you have terms in one polynomial, the same number of rows as you have terms in the other polynomial. Then work box by box, multiplying like you would with a multiplication table. Term by term, you multiply the term in the row of the box by the term in the column of the box, and the product goes in the box. Once all boxes have been filled in, you add all of the values in the boxes to get your solution. Take a minute to pause the video now and try solving the following examples. We can try factoring this first problem using grouping. So we're going to group together the x to the third minus x squared together, and then we're going to group the 3x minus 15 together. So from the first group, we can pull out x squared. So we end up with x squared times x minus 5. For the second group, we can pull out 3, so we end up with 3 times x minus 5. Then we can factor that to be x squared plus 3 times x minus 5. And if we check, that does equal x to the third minus 5x squared plus 3x minus 15. There are a few ways that we can try expanding this. The first one would be to take each of the terms from the first factor and multiply it by the second factor. So you would get 3a times 2a plus 5b minus 3 minus 4b times 2a plus 5b minus 3 plus 1 times 2a plus 5b minus 3. Then you would simplify, so you would get 6a squared plus 15ab minus 9a minus 8ab minus 20b squared plus 12b plus 2a plus 5b minus 3, which would then simplify down to 6a squared minus 20b squared plus 7ab minus 7a plus 17b minus 3. Another method that you could try using would be the box method. So one side of the box would be 2a, 5b, negative 3. The other side would be 3a, negative 4b, and 1. So then again, we would get the terms 6a squared, 15ab, minus 9a, negative 8ab, negative 20ab, 12b, and 2a, 5b, negative 3. So then again, adding this all together, we would end up with 6a squared minus 20b squared plus 7ab minus 7a plus 17b minus 3. For higher level classes, you may need to use long division to solve rational expressions. Long division works much the same way with constant numbers or polynomials. Take a minute to pause the video now and try solving the following examples. When we're doing long division of polynomials, we're going to write it out this way, so that 5x to the third plus 3x squared plus 8x minus 8 is inside of our long division symbol, and then it is being divided by 5x minus 2. So again, like normal long division, we're going to look for what do we need to multiply the first term of the divisor by to get what is on the inside, the first term there. So in this case, we want to think about what do we need to multiply 5x by to get 5x to the third. So here, that's going to be x squared. So we put that in this position. Then we go along and we multiply each term of the divisor by x squared. So we get 5x times x squared is 5x to the third, and then we get negative 2x squared. So we're going to subtract that from what's on the inside, and we end up with 0 plus 5x squared plus 8x minus 8. Then again, we're going to look at what do we need to multiply 5x by to get 5x squared. We'll need to multiply it by x. So we'll get 5x squared minus 2x. Subtracting that, we get 0 plus 10x minus 8. Again, what do we need to multiply 5x by to get 10x? That's 2. So we have 10x minus 8. Subtracting that, we then get 0 minus 4. So we're going to write this out as the fraction equals x squared plus x plus 2 minus 4 over 5x minus 2. We're going to write this next problem out. So then we want to look at what do we need to multiply y by to get 2y to the third. So we need 2y to the second. Multiplying out, we have 2y to the third minus 4y squared. So subtracting that, we get 0 plus 5y squared minus 13y plus 9. Then we want to look at what do we need to multiply y by to get 5y squared. So that would be 5y. So then we have 5y squared minus 10y. Then we're left with 0 minus 3y plus 9. We need to multiply by negative 3 to get negative 3y. So we have negative 3y plus 6. So we're left with 0 plus 3. So we can write that our final answer is 2y squared plus 5y minus 3 plus 3 over y minus 2. In this example, we write it out again. Then we look at what do we need to multiply x squared by to get 2x to the fifth. That would be 2x to the third. So then we have 2x to the fifth, and in this fourth power spot, we're going to put a 0x to the fourth, and then minus 4x to the third. So then we have 0 plus 4x to the fourth plus 0x to the third plus 0x squared minus x minus 3. So then what do we need to multiply x squared by to get 4x to the fourth? That would be 4x squared. So then we have 4x to the fourth plus 0x to the third minus 8x to the second power. So then we subtract that and get 0 plus 0x to the third plus 8x squared minus x minus 3. So then to multiply, we would want 8 So then we have 8x squared minus 16. Subtracting that, we get 0 minus x plus 13. So for our final answer, we end up with 2x to the third plus 4x squared plus 8 plus 13 minus x over x squared minus 2. Exponents move the variable up to the power. F of x equals a to the x, where a does not equal 0. Here, the base number stays the same, but the exponent changes depending on the x value you plug into the equation. X tells you how many times you multiply the base by itself to get your y value. Exponentials operate under the same rules as exponents. One specific exponential function that gets used a lot is the natural exponential function, f of x equals e to the x. Logarithm is the inverse to the exponential's function. It asks the question, what exponent produced this? Like exponents, logarithms have their own set of properties that we can use to work with them. Here are a few of them. Log to the base a of m times n equals log base a of m plus log base a n. Log base a of m divided by n equals log base a of m minus log base a of n. Log base a of 1 divided by n equals negative log base a of n. Log base a of m to the r equals r times log base a of m. In Calculus 2, you will learn an interesting technique to use these properties of logarithms to solve more complex problems. Take a minute to pause the video now and try solving the following examples. Using our logarithm rules, we can take these 3 logs that are added together and combine them into one log. On the inside of the log, we then multiply each of the original insides together. So we get log of 2 times 11 times 7, so we end up with the log of 154. To expand this logarithm, we can use the logarithm rules. So we see that the power on the inside can be brought out and multiplied as a constant on the outside. So then we're left with 6 log of 6 over 5. We can then split up into 2 logarithms because the inside is a fraction. So then we get 6 log of 6 minus 6 log of 5. Notice that you drag the 6 along to both logs. To solve this log, we want to first rewrite it. So we're going to take that outside 2 that is being multiplied and bring it in as a power. So we have log base 5 of x to the second power equals 10. So then, rewriting this, we can use the fact that when we have log to a base of something equals something, then the base stays as a base, and whatever it is equal to becomes your exponent, and then whatever the inside is what is equal to it. So here we get 5 to the 10th equals x to the second power. So then we can solve from there. So we can take the square root of both sides and we'll end up with 5 to the 5th equals x. And then we get that x equals 3,125. In this case, we don't take plus or minus because The original function had x on the inside of the log, and so the log domain does not allow us to have an x that is negative. We're going to again use the properties of logarithms to simplify this expression. So we bring each of the constants inside as powers. So we're left with the natural log of x to the 6th plus the natural log of x to the 9th minus the natural log of 3x plus 2 to the 7th. So then we can bring the two that are added together in as one that is being multiplied on the inside and the one that is negative down as what is being divided on the inside. So we get the natural log of x to the 6th times x to the 9th divided by 3x plus 2 to the 7th. All of that on the inside of the natural log. And then simplifying one further, we can have the natural log of x to the 15th over 3x plus 2 to the 7th. For this example, we're going to combine the two logs first before we solve. So we end up with log base 2 of x squared minus 6 divided by 1 minus x, all equals 3. So then again, rewriting this, we get 2 to the 3rd equals x squared minus 6 over 1 minus x. So we end up with 8 equals x squared minus 6 over 1 minus x, and then multiplying both sides by 1 minus x, we get 8 minus 8x equals x squared minus 6x. Moving everything to one side, we get 0 equals x squared plus 2x minus 8. Factoring, we get 0 equals x plus 4 times x minus 2. So our two possible solutions are x equals negative 4 or x equals 2.